Hello students, in this lecture I will be discussing about disaster resistant house construction, which is in module 4 your disaster management audit course. A large portion of the wealth of any nation is invested in its built up environment like housing, infrastructure, industrial and commercial facilities. The quality of this built up environment expressed in terms of durability, safety and functionality, and these are the determining factor of the quality of the life and economic development of that society, and the competitiveness of industry and services depends upon their infrastructures. So the extensive loss of this wealth is caused by natural disaster that may strike periodically. So these natural events causes sudden destruction, damaging the society and the social structure and economy on a massive scale. So this lecture deals with the traditional as well as modern disaster resistant construction techniques to meet the aftermath of a disaster, and also examines the issue of damage to reinforced concrete cement, that is RCC buildings, by underlying the necessity of adherence to building codes and standards. Some recent advances in housing technology are also discussing in this lecture. So the reason for intensifying the impact of disaster are mainly the improper location of the building, the faulty design and use of poor quality materials, and substandard construction practices, non-compliance to building codes, lack of awareness of safe construction practices and disaster resistant practices. We see few guidelines for disaster resistant construction. The behavior of a building during any disaster depends critically on its location, overall shape, size and geometry. Hence, at the planning stage, architects and structural engineers must work together to ensure that the unfavorable features are avoided and a good building configuration should be chosen. For safe site selection, a few points should be kept in mind. That is, safe site which is away from landslides, so steep slopes, falling blocks, loose soil and polluted water. Should avoid the site which is near to these prone areas, and well drained areas to avoid risk of waterlogging and vector-borne diseases. For earthquake resistant construction, it is better to avoid hillside slopes and areas having sensitive and clayey soil. It should be preferable to have several blocks on terraces rather than one large block with footing at different clusters. The building as a whole should be kept almost symmetrical. Simple rectangular shapes have better in an earthquake than the shapes with multiple projections. And separation of a large building into several blocks is required for symmetry and rectangularity of each block. And restricting the width of the openings using the bond beams and taking recourse to steel or wooden dowels as well as RCC band at plinth, lintel and roof levels are good disaster resistant techniques for building in the case of earthquakes. In the case of cyclones, structures should be erected in areas which provide a protective shield from high wind with natural firm level foundation. Flat roof arrangement should be avoided. So should be the projecting elements like antennas, chimneys, eave projections, sunshades, etc. will be the suitable in cyclones prone areas. The construction should have adequate diagonal bracing, reinforced masonry, thicker plate glass, and anchoring of purlins to gable ends. These all are should be taken care of in the structures made in the cyclone prone areas. As far as the flood resistant housing is concerned, prohibited zones should be totally avoided. Layout of the buildings, houses should be such a way that they do not block free flow of water. The construction should be done on raised mountains. Waterproofing treatment, adequate bracing, afforestation in catchment areas are required for flood prone areas. We will see few traditional disaster resistant construction techniques. Several earthquake prone regions in the country have traditionally built houses and that minimize the damage to life and property and stand up well in earthquakes. So the traditional wisdom and attention to detail can be applied to modern material as well. So these techniques are based on the use of traditional materials like timber and bamboo for building houses. So avoiding the compression structures like domes, arches is another option. The structural system needs to be tensile and the material should be flexible. As in the case with timber, steel and bamboo, it is flexible kind of materials. It also helps if the structure is constructed in a way that it vibrates as one unit and sways it together during an earthquake. Most new constructions with heavy roofs, slate, tiles or RCC supported with weak walls have proven deadly effect in earthquakes and all. Older houses at high elevations have timber roof held together by timber and tie bands. Horizontal timber beams which spanning across the entire building, connecting the entire structure and giving it the character of a cage. So such houses have suffered little damage despite the mud and stone masonries. So the earthquake resistant houses should have tie bands just above the level of the floor, at the level of the doors and also the windows, and another at the roof level. And corners are the most vulnerable and should be strengthened. The elasticity of the structure can be enhanced with flexible steel rods or wood materials at corners. The doors and windows should be very few, small and symmetrically placed away from the corners. The houses should be as light as possible. It should not be heavier structures. The earthquake resistant structures adopted at Rajput families of Rajasthan in India is called summers, and chaukats or khoti is the traditional building technology adopted in Himalayan regions. Koinja is the building technology adopted in North Peru regions, and it's a flexible structure with an inherent earthquake resistance. So these type of structures have proved to be quite resistant to earthquakes, and the design and techniques behind them could be used in the present context. We will see few retrofitting measures for hazards. It is in the we'll see in the case of storms or cyclones. Wind shielding buildings. This will protect from cyclone. So you can see here the protection of house by some hillock or deep rooted tree. These are act as the shield from the storms, and it will protect the infrastructure. And there should be a desirable plan for reducing the cyclone damage. Like symmetrical building are more stable compared to these asymmetrical structures. And if the building is constructed in a ridge, it will attract the storms, and the damage will be more in this kind of buildings. So this building is constructed in valley, so it will protect it from a storm. And the group planning can reduce the effect of the storms. If the buildings are in a row pattern, which create a more wind tunneling effect, which results higher damage compared to a zigzag planning will reduce the damage, and it will not create a wind tunnel effect. This is an example of retrofitting measures for flood prone area. The construction at low level enhances the effect of the risk. High risk will be high risk. But if it is, the building is in a natural elevation, or if it is not available, we can make a artificial elevation, and it will protect the building or the infrastructure from the flood. These are the few retrofitting measures in the building of an infrastructure. There is a large overhangs. It will easily get broken, and it is better to avoid large overhangs. And the type of roof should be take care of in a construction. The type of roof you can see here. If it is not holding, the roof sheets may fall off, like in this case, and the lifting may happen to the roof, and this may not be holding to the wall. If the holding is inadequate, the roof will fall off easily. So the roofing should be considered in an wind prone area. We will see the damage to reinforced concrete, cement or RCC buildings. So no building can remain entirely free of damage during a high intensity earthquake. Nevertheless, all houses, big or small, can be made safer or earthquake resistant. Structures can be made to withstand earthquakes of a particular magnitude by taking certain precautions. The buildings generally collapse as a result of inertial forces. So during an earthquake, the lower part of the building tends to vibrate as it is in direct contact with the ground. So the forces of inertia, however, keep the upper motion static. So this conflict of forces led to collapse. So the magnitude of these forces is directly proportional to the weight of the building. So the heavier the structure, the greater will be the damage. If the structure is light, lesser number of people die in the case of a collapse. So it is necessary to provide horizontal reinforcement in walls for imparting bending strength in the horizontal plane against plate action for out of the plane inertia load, and for trying to perpendicular walls together. So it is provided in the form of few bands to hold the structure together, like plinth band, lintel band, roof band and gable band. So actually band is a reinforced concrete beam provided continuously through all load bearing longitudinal and transverse walls at a given level. We will see the building codes and standards. Building codes are the standards and the guidelines for construction of buildings to ensure a minimum level of safety for the occupants. An appropriate building code incorporates through understanding of the forces that the natural hazard impose on the area governed by the code. So the building codes are only one of the tools for increasing the resilience of the built up environment in the face of a natural hazard. So land use planning, emergency management, natural resource protection and infrastructure development policies play significant roles along with these building standards. Coordination of all these activities can be achieved through comprehensive hazard mitigation planning. It is never possible through any building standard to lay down some regulations for protection and infrastructure from earthquakes of all magnitudes. It is not possible to build earthquake proof buildings. However, the design approach adopted in the building code is to ensure that the building structure possesses minimum strength to withstand minor earthquakes which occur frequently with some non-structural damage. And the building structure possesses the resistance to moderate earthquakes which occur once in 10 years or so with minor structural damage and some non-structural damage. And the building structure possesses withstanding capacity to a major earthquake which is likely to occur once in a lifetime of the structure without complete collapse. The Bureau of Indian Standard has initiated several pre-disaster mitigation projects to reduce the impact of natural disasters on life and property as well as bring down social vulnerabilities. It has undertaken standardization efforts in the area of earthquake engineering. There is an example of BIS standard that is IS 13935 1993 which covers the selection of material and techniques to be used for repair and seismic strengthening of a damaged building during the earthquake and retrofitting for upgradation of seismic resistance of the existing buildings. The Himalayan region or Indo-Gangetic plain of Western India, Kutch and Kathiawar region in Gujarat are geologically unstable part of the country. Hence, some devastating earthquake of the world has occurred in these places. Strong earthquake have also visited a major part of Indian peninsular India. But these have been relatively few in number and of considerably less intensity. So, taking cognizance of their frequency and intensity, it is thus all the more important to follow the building codes and earthquake resistant designs more rigorously. We will see few recent advances in housing technology. The technologies that are innovative and earthquake resistant need to be made use of in order to cope with disasters like earthquake and cyclones. And first is base isolation technology. Reducing the forces transmitted to the building from the ground by placing the building top of a mechanical system of isolators, sliders and dampers, which is called base isolation technology. This dampens the violent movement of the earth during the seismic event. By using isolators, the building is decoupled from the ground motion of any earthquake and transmission of seismic energy to the building. This is done by lowering the vibrational frequency, allowing the building to move or displace. And it is lowering the shock acceleration of the seismic event and reducing the tendency of the upper floor to move faster than the lower floors. And it is able to displace the horizontality in any direction by 24-inch from the center. And next type of advanced structure is insulating concrete forms, ICFS. These are able to resist natural hazards such as hurricanes, earthquakes, tornadoes, floods and fires. And ICF construction is relatively new to the building codes and home building industry of the United States. ICFs are hollow foam blocks or panels that stacked interlock to create exterior wall of the building. So reinforced concrete is then placed inside the form blocks and creating strong insulated concrete walls. ICF construction is already noted for benefits such as energy efficiency and durability. And next type is reinforcing concrete. The most widely accepted form of reinforcement is welded wire fabric, WWF. It is a mesh of thick steel wires that is placed in concrete. However, synthetic fiber reinforcement avoids the increased labor cost and difficulty in placement that are associated with WWF, and small diameter synthetic fibers are now being added to concrete in order to reduce the shrinkage and cracking by more than 80%. And next type of building is cyclone resistant dwelling construction. This technology has been developed by the National Building Construction Corporation, and which involves the use of pyramidal roof so that the thrust area is reduced and tile used to give the roof the required shape is made possible. The walls and foundation have been well spaced to allow for flexibility when a building is buffered by strong winds. Such building techniques are commonly used in earthquake-prone areas in Japan along California coastline of US. Next type is disaster-resistant pier systems. In earthquake-prone areas, disaster-resistant pier systems are generally considered to be more cost-effective than ground anchor systems, which do not always perform adequately. The anchors are usually located on the longer side of the house, which bear the greatest wind load. However, earthquake loads can occur in any direction, and additional anchors on the short sides increase the cost. Because the piers are usually separated from the soil by pads, rust and deterioration are not such a big concern, and they are for ground anchors. These are the references. Thank you for listening.